I hope you're ready to tackle some big bears, because tonight we're going after the remainder theorem. And I hope by the end of tonight's video, you're going to think of the remainder theorem as a valued ally that you can use as a great shortcut to tackle just the right questions. So here's our fundamental definition, and this will lay the groundwork for what we're going to tackle in the future slides. So first off, if a polynomial, we'll name him p of x, is divided by one of its linear factors, then the remainder is guaranteed to be what? Now the key word here is factor. So as long as it's a factor, then the remainder is guaranteed to be 0. Now let's assume that we have some quantity, we'll call it x minus a, and we know that he is a factor of the polynomial p of x. If you were to evaluate p of a, the answer is again guaranteed to be 0. Now let's look at our first live example here, and I'll give you two options. One's going to be significantly shorter, quicker, more efficient than the other. So we've been given a polynomial. In this case, it's a cubic polynomial. We've got a degree 3 up here. We know that this polynomial is guaranteed to have 3 linear factors, and it should have 3 roots. And the question is the quantity x plus 1 one of his linear factors? So one option is to go through the entire process of long division. Not impossible. In fact, I'd put big money that you'd get the right answer when you were all said and done. But it's going to take a lot longer. The more efficient path here is to try to use the remainder theorem. So basically what we know, if I evaluate, it's not p this time, it's f. If I evaluate f of negative 1, if the answer turns out to be 0, then I can say yes, x plus 1 is a factor. Okay. However, if I evaluate f of negative 1 and I get anything other than 0, then my answer would be no, x plus 1 is not a factor. So that's what we're going to try to do. We're going to jump in, evaluate it, and then make a conclusion that falls into one of these two categories. So let's go ahead and substitute negative 1 into the function here. And we've got negative 1 cubed minus 2 times negative 1 squared minus 3 times negative 1. And you're more than welcome to use your calculator to evaluate this bear. And it looks like I did get an answer of 0. So my final conclusion is yes, x plus 1 is a factor. And then one other thing they may ask you to do is then to say, okay, well, if we know that x plus 1 is a factor, what are the other two factors in this particular case? And we go ahead and actually perform our long division, and we'll address that towards the end of the video tonight. In this example, we're going to swerve away from the algebraic approach that we saw in the last example and take a strictly graphical approach, which I think you'll find more convenient. It's certainly quicker, less time consuming even than the last. So what they're saying here, or asking, so we've been given a polynomial named p of x. So this rascal here, we've got p of x. And what does it say? And we don't even know who the equation of p of x is. That's the beautiful part about this problem. All we've been given is this graph. What if p of x was divided by the quantity x plus 2? Okay. We want to know what the remainder would be. So let's see. If I divided by x plus 2, the remainder is guaranteed to be equal to whatever p of negative 2 is. Now notice if you have a plus 2 up here, I'm evaluating negative 2. It's kind of like you're always asking yourself, what would the 0 be based off of that factor? And that's the number you end up plugging in. Now if you look at your graph, right here at negative 2, looks like I'm estimating that the answer is about 9. So we'll say p of negative 2 is equal to 9, and that's the remainder that you would get if you divided p of x by the quantity x plus 2. Okay, let's take a look at the next one. Let's see, if you divide it by x minus 2, what you want to do here is evaluate p of positive 2. We'll check out that graph, and it looks like the value is at 11. So again, that is your remainder value without actually performing your long division. Last but not least, if I divide it by the quantity x minus 4, I want to evaluate p of positive 4. Let's check out that graph, follow that bear up. And it looks like we're sitting in a value of 14. Here's our last big bear of the night, and I think this does a good job of simulating a part 3 question that we could see on one of our exams. First out of the gates, we've been given a function named g of x, and we want to determine whether x plus 4 is a factor or not. So the first thing I'm going to do is evaluate g of negative 4, and we're going to substitute that for each and every x. So we've got negative 4 cubed plus negative 4 squared. And like we said earlier, you're more than welcome to use your calculator to carry out these calculations. We've got negative 64 plus 16 plus 40 plus 8. And by the time I combine all of those like terms, I did indeed get 0. So I'm saying yes, x plus 4 is a factor of g of x. Okay, now that's a really good thing. And now that we know that x plus 4 is a factor, we can kind of build off of that and determine who the other factors are. Now keep in mind, how many are you expecting total? We are working with a third degree polynomial, so we are guaranteed that there's going to be 3 distinct linear factors here. And we're going to go ahead and figure out who the other 2 are in addition to the x plus 4. Now there is no shortcut around this process. We are going to have to do our long division. Okay, so let's go ahead, try your long division on your own, and we'll come back and we'll see if we got the same quotient. So you see what I've got cooking here. We just finished my long division. Tried to color code it a little bit so you could follow each phase of it. But you'll notice, most importantly, I did get a remainder of 0. If you got anything other than 0 right here, it would have contradicted what we had done earlier, and there obviously would have been an error somewhere that you could backtrack and try to figure out. So what you're seeing here is that this is your quotient. This is where you want to focus. This is what we're going to continue to factor to find those other factors. And here's what I like to write really quick, just to kind of draw it all together and keep the big picture in mind so I don't lose sight of exactly what it is I'm accomplishing. Okay, here's the original g of x function, right? What have we determined so far? He's equal to the product of x plus 4 and the new binomial, or I should say trinomial, x squared minus 3x plus 2, okay? And I can just carry down this linear factor, and I'm thinking multiply, add, multiply, and I know I need an x times an x as the multiples. I know I need negative 2, negative 1. Beautifully, it works perfect. Here are the 3 linear factors of the function g of x. Oh, whoops, I might have lied. I got to sneak in one more slide here, one more example. We've been given h of x here, another cubic function, and now the question is the 3x plus 2 a factor? Now what makes this one extra challenging is this coefficient of 3. What exactly do I plug into the function h to test whether this is a factor or not? Any predictions? What would you plug in? Okay, just pretend like you're looking for the 0. What if I set this 3x plus 2 equal to 0? What would you get for x? Okay, so what you'd simply get is, let's see, subtract the 2, divide by 3, you'd have negative 2/3. This becomes the number that I would plug into h to test whether 3x plus 2 is a factor or not. So let's evaluate h of negative 2/3. We're going to make this substitution across the board for every x, and now I really want to use a calculator to carry this one out. Oh my goodness, I'm going to run out of space here. And we'll get a plus 10. And once I did plug this all into my calculator, I did get 0. And again, so now my conclusion is yes, 3x plus 2 is definitely a factor due to the remainder theorem.